So let me just address one or two of the questions or queries that were raised in the previous class. Perhaps I didn't explain them as well as I should have. And this was the question pertaining to diagrams and cutting diagrams and to get the actual unitarity relation. It's actually very explicit for the case of the scalar form factor that we had, where we wrote down this expression as 1 plus s by 16 pi squared f pi squared times L4 bar minus 1 plus 2s minus m pi squared divided by f pi squared j bar of s, and j bar of s is our old friend 1 by 16 pi squared, and this is sigma of s logarithm of sigma of s minus 1 sigma of s plus 1 plus 2, and sigma of s is equal to square root of 1 minus 4m pi squared by s. Now the reason why this picks up an imaginary part is that sigma of s is less than 1, and this quantity minus 1 is negative. This thing of course is positive, and because of the minus sign there, it produces that I pi that is of interest to us. So this is the tree level contribution, and at one loop, this is like this, and this is where the cut diagram comes in, and then this is exactly what you started out with. So this is the gamma bar s tree, and this is the pi pi scattering T00 of S tree. Okay, so this should answer the question that was asked by Biswajit over there as to what is the connection between these two. However, it's not the same for the electromagnetic form factor, because in chiral perturbation theory, it has contributions that come like this. So there's no obvious way of cutting the diagram for the electromagnetic form factor. Nevertheless, the relationship holds. So in other words, one should not take these kinds of cutting diagrams and all too seriously. It's the mathematical relationship that is more important, and it almost always works. But here's an example where it's not that obvious, because the couplings of the photon to the pion are more complicated in chiral perturbation theory. Nevertheless, the unitarity relation holds. It has to, and that's simply the truth. Now, there's a question that was routed through Namit about an explicit calculation for some of these dispersion relations. So what we have done so far is we have looked at, from Zwicky, we looked at the two-point function, and then we looked at form factors in general. Then there, of course, the simplest thing is we always know how to write a dispersion relation for this. Nevertheless, we found this amazing result here, which was the omnis solution to the form factors, okay, and which you can obtain in terms of the phase alone in the elastic case. This is the very nice thing, and all the pieces of information go into that, which is that of elastic unitarity, and what else went into it, and the fact that these are real analytic functions. These are all ingredients which go into the construction of the form factors in general, okay? So here we are talking about perturbation theory, and I've been screaming since I met you all that we can get the imaginary part of this J bar S from this particular thing. So now let me turn this question around and ask you, if you know the imaginary part of this J bar of S, how do you get J bar of S? Through a dispersion integral, okay? Now one of you has to try to help me to get J bar of S knowing the imaginary part. What's the imaginary part of J bar of S? It says don't cross. I don't think anybody meant. Oh, it's probably the camera that's the problem. Yeah, oh yeah, so that's why it says no. Okay, so I ask you, imaginary part of J bar of S is just pi times sigma of S, right? So I ask you now, if I know imaginary part of J bar of S, how do I get, if I know this, how do I get this? Using dispersion relation. I was asked a question, can you do an explicit example of a dispersion relation? Well, here is one, the simplest building block of all of perturbation theory. Now, let's say that you have a subtraction. So let's say that it's J bar of S. So then there's got to be an S by pi like this. And then there'll be an integral along the branch cut. And where is the branch cut starting for this one? It's obviously starting at 4m pi squared to infinity. And let's do an integral along the line ds prime, then pi sigma of s prime divided by s prime minus s. Okay, so here is an example of a real life dispersion integral, which will allow you to reconstruct the function from the imaginary part. Okay, so this has to hold. This is true. Now, if you do this, go back home and do this on Mathematica, put it in, and test all the properties for yourself. Ask yourself, what is the value of the function if you're coming from above onto the branch cut along the real line? Supposing you come from above, suppose you go from below, play around with this, and you will see that all the properties that have gone into the construction of these things can be explicitly checked for this particular case. Okay, so that's a kind of exercise that you should do. Yes.
Just subtract it out in finite A0 and the rest.
Yeah, it's a subtraction just to make sure that the thing converges. That's all. Yeah. I mean, if you didn't do that, then it won't converge, and there's a contribution from infinity, and you don't know what it is. So this has to be true. Assuming that one subtraction suffices. If that doesn't suffice, then you have one more subtraction constant, and then you do whatever it is that you have to do. Now, this was very nice. This is the dispersion relation for a form factor. Now, if you want to do a dispersion relation for a scattering amplitude, it's already a little more difficult because it's going to be a function of two variables. So let us ask ourselves, what are dispersion relations for scattering amplitudes? Dispersion relations for scattering amplitudes. And let's think of a function t, which is a function now of two variables, s and t, and then there's always a u hanging around, which is constrained by s plus, constrained by the requirement that s plus t plus u is equal to 4m squared. Now here we are looking at scattering of equal mass particles, scattering of equal mass particles. But this presence of this u is going to make itself felt when we write down this dispersion relation for this. I'm going to ask you, let us say that this thing converges very nicely far away. So what I need, of course, is the complex S plane, because I'm going to keep T fixed. So this is an example of a fixed T dispersion relation. These are the earliest ones to be proved. And so if you say T is fixed, after that you have only one variable. So you may say, hey, why don't I write down a dispersion relation for this thing? Exactly as I wrote for the form factor. So what would I have to do? I have to first identify the branch point. And there would be a branch point over here. And then there would be a branch cut starting over here. Fine. So let's do that as we did for the form factor. And then we have a curve like this that goes up like this. But unlike in the case of the form factor, there's going to be one more branch cut. And where is this branch cut going to be? I'm going to ask you people where you expect such a branch cut to be, and why should there be such a branch cut? There is such a branch cut because you have three Mandelstam variables over here for fixed T, but there's U also. Nobody told you that you have to have a dispersion relation in S. You may as well have had a dispersion relation in U, right? At fixed T, you may have had a dispersion relation in U. There's nothing to tell you that S is any more distinguished than U. So there's something going on in this variable S, there must be something going on in the variable U also, which means that U also would have a branch point and a corresponding branch cut. So when viewed in the S-plane, there'll be another branch point over here. So this is the origin and it's going to be here. And then there's going to be a branch point, the branch cut like this. So your contour that you're drawing over here comes, and then it has to hug the real axis over here again, plus I epsilon, come all the way around, do this all the way here, and then come back and join it over here. Okay? So just based on this kind of heuristic argument, you can say that, look, unlike in the case of the form factor, where there was only a cut on this side, which part of the y-axis is this? Somebody tell me which part of the y-axis is this? This is to the right, and this is to the left. Okay? So the form factor had only a right-hand cut, whereas the scattering amplitude will have a right-hand cut as well as a left-hand cut. So let us write down what these things are and how does this go. So we also have to keep an eye on what happens with this direction of this integration. So this integration is like this integration is like that, then this integration is like this integration is like this. I had said in the context of the form factor that it was very important for us to apply the Schwarz reflection principle, which did some wonders for you. The Schwarz reflection principle said that if you approach the cut from here and you approach the cut from here, then the difference between the two is going to be twice the imaginary part, isn't it? And you'll remember that. So the Schwarz reflection principle requires that the domain where this function is analytic must necessarily contain a part of the real line where the function is real. And so it is for the scattering amplitude also. There's a part of the real line where the function is going to be real. So the Schwarz reflection principle holds for this also. And therefore, you're justified in saying that the contribution that is coming to the integral from this part is again going to be twice the imaginary part. And this is also going to be twice the imaginary part along this. So whenever we write down these seemingly simple and very glib expressions, you have to be sure that you know what you're doing. So here, let me name this as SR as the branch point, and let me call this as SL as a branch point like so. So this is an integral from minus infinity to SL, L standing for left. I saw that here also we have Nambu left and Nambu right, because it's a chirally invariant building, I suppose. Therefore, we also better have, chiral symmetry being respected by our amplitudes also. We don't want to tease off any of the big guys. T prime. Now, every single thing that I'll write here actually has to make sense. So when you say that you're going to evaluate these dispersion integrals, you have to say from which direction you're approaching. Okay. So this again has to be S prime plus I epsilon at that fixed t divided by the Cauchy kernel, which is S prime minus S ds prime plus 1 by pi times integral of SR infinity imaginary part S prime plus I epsilon t divided by S prime minus S ds prime, imaginary part of t. Okay, but this, again, we have to keep in mind that this is the absorptive part in the S channel and this is the absorptive part in the 2 channel. Now, if you didn't know from the beginning that it is possible that in quantum field theory, the crossing property holds, then a priori you do not know whether these 2 things are going to be related to each other or not. But definitely in the year 2024, We know that the crossing property has been proved rigorously, and therefore we know that it's possible to obtain the absorptive part. I'll keep calling it absorptive part, imaginary part, keep using these terms interchangeably, that it's possible to go from one to the other because of the proof of the crossing property. The crossing property is associated with the fact that the scattering amplitudes in each of the channels, what channels? STU channels can each be obtained as boundary values of the same function, which may be analytically continued from the physical region of one to the other, Now, this was not at all obvious, and it had to be proved rigorously, and this is the work of Bro, Epstein, and Glaser. And this follows from the theory of several complex variables. And is very nicely described in one of the sections in Itzikson and Zuber. C section, don't remember the number, in Itzikson and Zuber. I think for any spins, it can be extended. Spin and all is not directly related to this. Those are representations of the Lorentz group, so there is no problem as such. So, so the statement is that it holds for all of them. Okay. There might be. Of course, this is based using current commutators and commutators of fields. There would be corresponding. You're asking a very important question. These things, one has to look in and see where they're discussed, how it holds for fermions, how it holds for. Yeah. And then there's a, remember that there was something called the Lyman-Chelin representation for form factors. There's an analogous one for scattering amplitudes, which is the Yost-Lyman-Dyson spectral representation for scattering amplitudes. And for, so that was for 2-point functions. For 3-point functions, if I'm not mistaken, the corresponding representation in field theory is due to Gilbert, Deser, and Sudarshan. Again, this is a part of history that you people can study to motivate your own interest in these topics. Okay, so what I'm saying here is that it is possible to write dispersion relations for scattering amplitudes, but they are intrinsically more difficult. Nothing could have been easier than what we did for form factors. Okay, so once you write down in perturbation theory a dispersion relation for the J bar of S, you can get a result for the form factor in terms of this dispersion relation. After all, this is the only imaginary piece. Nothing else is necessary. Okay, you're not able to predict the polynomial pieces, but a general polynomial, in this case, a linear piece in S is present. But the actual structure, the interesting structure involving real and imaginary parts is coming from this J bar of S, and this J bar of S respects or obeys a dispersion relation. And therefore, from the imaginary part of this J bar of S, you can reconstruct any form factor of interest to you, and you can predict its structure, okay? Now, nothing could be simpler than the form factor. So I'm going to ask you, do you think that such a thing can be done for scattering amplitudes also? So this was a very simple case of a scattering amplitude where I have written down an example where there is no isospin, no other internal quantum numbers, just one scattering amplitude, and this is what it looks like. But we should try to make life a little more interesting and then deal with real life situation like scattering of pions. And I was glad to see that the blackboard had many of the expressions that I needed. And by now we all know that the scattering amplitudes of interest to us, at least in this course, are these amplitudes of definite isospin T0 of STU, which we said can be written as 3 times ASTU plus ATUS plus AUST. Now this is algebra, but beyond this also we will need some of this information in order to write down a suitable dispersion relation for these scattering amplitudes of pi-pi scattering, because the pi-pi scattering is a system of scattering amplitudes, a system of isospin amplitudes. So the question is, what is the corresponding bunch of imaginary parts appearing on the right-hand side? Because one of them happens to be in the S channel, another is in the U channel. And this is an example of an unsubtracted dispersion relation. Life is going to become more complicated when you have to bring in subtractions also. So let us go here, STU. Yes, minus T. So later we will find that keeping it in this terms of this AS and AU and all is very complicated. So we will replace all this U channel and all by suitable crossing matrices and then express everything in terms of the absorptive part in the S channel. So that is why I have to do this gymnastics before I can write down a useful form of dispersion relations for the system of pi-pi scattering amplitudes. See, everything here that we are saying, every word has some sense. It's a system, not just one, okay? And if you say U channel, how to express that U channel absorptive parts in terms of S channel absorptive parts? The answer is through objects that will allow you to go cross from the S channel to the U channel, okay? So here you have a system with 3 amplitudes in the S channel. So you need to go to 3 amplitudes in the U channel. So if you have 3 objects on the left-hand side, 3 objects on the right-hand side, how do you go from one to the other? You multiply it by a matrix. What should be the dimension of that matrix? A 3 by 3 matrix. So we have to invent 3 by 3 crossing matrices with the right properties, starting from this basic definition, which has this 3, a 1, 1, and this other thing which you know, A, T, TUS, minus A, UST, and then you have T2S of STU equals A, TUS plus A, UST. It's also good to keep in mind that we had this pi 0 to pi 0, which is a totally symmetric amplitude, which was T0 plus 2, T2, like this. On the other hand, if I take 1/3 of T0 minus T2, what do I get? 1/3 of T0 minus T2. Just look at this and tell me. It'll give me the A, ASTU. And the way in which you get these is through projection matrices, and I'll write them down for the original scattering that we had, pi A, pi alpha, pi beta, going to pi gamma, pi delta, is the projection in the S channel of definite isospin 0 is 1/3 of delta alpha beta, delta gamma, delta. Then I need 3 such projection operators, and this is transforming as a trace. Okay, that's why it has I equals 0. This thing is I1, and it has to transform as a vector under these SU2. I think the previous lecture also had some of these things, so it makes life a bit easy for me. Minus delta, well, as easy as it can be, I suppose. P delta, like this. And finally, I have P2 of S, P2 S, which is given by 1/2 of delta alpha delta, delta beta gamma, plus delta alpha gamma delta beta delta, minus 1/3 of delta alpha beta delta alpha gamma. The way in which you look at this is you're multiplying two iso vectors, okay? So from that, you're supposed to get isospin 0, 1, and 2. One of them will transform as a traceless symmetric part. One will transform as antisymmetric, also a vector in this case, and one is just the trace part, okay? So that is why you get the total isospins of 0, 1, and 2. And when you use this and you contract it with the original definition of the matrix element, which was delta alpha beta, delta alpha gamma, ASTU, plus various combinations of this, and you hit them with each one of these, then you will get this factor 3, 1, 1, etc. And then you can also check for yourself that these will respect the identities that any decent projection matrix is supposed to do, which is that the square of this, what are the properties of a projection matrix? Somebody has to tell me. Square of a projection has to be itself, right? This, when you square it, it has to be itself, right? You project something and then after there's nothing to project it further to. That's why p squared is p, okay? So each of these, the squares will be p. And what can you say about this and this? That they would be orthogonal to each other. So you can check all these identities. Then you have to be able to go from one channel to the other. How to go from one channel to the other? So this is the S channel. If I want to go to the T channel over here, it corresponds to the swapping of S and T, interchange of S and T. So then you'll get 3 times ATUS plus ASTU plus AUST, okay? That's what will happen under the interchange of S and T. You already know that ASTU is invariant under the interchange of the last 2. Okay, so this matrix that I was talking about for crossing from one channel to the other, we can explicitly see what they are. CST is 1/3, 1, 5/3, 1/3, half, minus 5/6, 1/3 minus half, 1/6. Now I ask you a simple question. What happens when you cross T and U? When we cross T and U, we already said that the isospin 0 and the 2, nothing happens to them, right? Under TU interchange. So that will therefore be 1, 0, 0 and 0, 0, 1. But what happens to the isospin 1 combination under the interchange of T and U? It changes, flips sign. So this gives you a 0, minus 1 and 0, like this. And then finally, there is the process of going from S to U looks quite close to CST, and it differs from this only in some signs, minus 1, 5/3. These signs change over here, minus 1/3, half, 5/6, and 1/3, half, 1/6. Supposing I cross from S to T and then cross back from T to S, then what happens? Supposing I go from S to T and go back from T back to S, then it's as good as nothing having happened, right? So what would you expect is a property of CST squared? CST squared should be identity. So you can check that this is the case. And supposing you went from CST and then went from ST to TU, that means that it's a repeated way of crossing from one channel to another. So there are also properties of closure of these matrices among themselves. Square of this thing is obviously identity. Go from T to U and you go back from U to T, you get back what you want. So these are all things which are, of course, best checked on things like Mathematica. It's a lot of fun. Okay? Well, at least I think it's a lot of fun. Now I want to kind of discuss an extraordinarily important result, which is very old, but still keeps coming back because these days, all these people who do conformal bootstrap and this and that and gravity, they all want to use constraints from the old days of axiomatic field theory, generic constraints, independent of the model, etc. So you will often see papers in the literature that cite these old papers. Of course, they don't go into the derivation of these things. And one of the basic fundamental results in all this investigations is the existence of what is called the Froissart bound. The Froissart bound is also important for determining how many subtractions are needed for this thing, okay? And it's a beautiful illustration of many of the ideas that we have been toying with in this course, not the least of which is the property of positivity. Now, somebody remind me, what is this positivity that I was talking about? Positivity. This is not a self-help course where we feel positive about everything around us. Well, we do feel positive too. But somebody tell me, what is the key result that we have that brings in this word positivity? And this was an application of unitarity, which can either be done at the level of the amplitude, or it can be done at the level of the partial waves, partial wave amplitudes. And you will all recall that the partial wave amplitudes, Ti of STU, arose up to some factor 1 by 32 pi, let's say sigma 2L plus 1, PL of cosine theta, and FIL of S, where we said that this cosine theta was T minus U by S minus 4M squared. Okay, so that is what we said. And then we said that there has to be, if you use this and then impose unitarity, which is that SS dagger is equal to 1, then the best expression, simplest expression of partial wave, expression of unitarity constraint shows up with partial wave amplitudes, and even more so in the elastic region. So this is imaginary part of TIL. Now remember that all these unitarity relations ultimately produce an imaginary part on the left-hand side and something on the right-hand side. And the something on the right-hand side typically is a product of various amplitudes, or it could be the same amplitude, or if it was imaginary part of the form factor as we saw, it involves both the form factor and the scattering amplitude, for instance. So this, we said, is something like this, where again there is a nu symbol over here. So this nu is Q squared in the units of the pion mass squared, like so. And what else did I need? Q squared itself is S minus 4 mu squared by 4. Okay, one has to get used to all these multiple symbols representing more or less the same thing. So this is TIL of nu squared, and in general there's one more factor over here. So this is some identical particle factor. Okay, please look at this and tell me what is the property of positivity that you see over here? What is the property of positivity that you're seeing over here? This imaginary part here is greater than the square of some quantity, okay? So this imaginary part is always positive. You have the equality sign if it is elastic, and it has a greater than or equal to sign when it is inelastic. If it is inelastic, you have two parameters. One of them is a phase shift, the other is the elasticity parameter. And the way it manifests itself is that in the Argon plane, when you cross the inelastic threshold, it goes into the Argon circle, okay? Thereby proving that the imaginary part of TIL is greater than the square of this. Okay, good. Now what this is telling you is that now if you take the imaginary part of the amplitude, and you insert a partial wave expansion for the imaginary part of the amplitude, then it will be a sum that involves the imaginary parts of the partial waves. And each one of the terms is positive. Therefore, the sum is also positive. So the great thing is, if you have dispersion relations like this, the positivity constraints that people talk about is associated with the fact that you have integrals of this type, where there's an imaginary part of the amplitude, which when projected onto partial waves is such that the partial waves here are always positive, because this whole thing is always positive because of the squares. And this is, of course, especially true if you take the forward scattering amplitude and put this t equal to 0. So there's no contribution coming from the Legendre polynomials, which will mess up things for you. Okay? So that's where this thing is coming from. Now, I want to prove this Froissart bound, and you people are going to help me prove this Froissart bound. Okay? So here, there's also one more step before that, which is the which has to do with the convergence of the partial wave expansion, convergence of the partial wave expansion. Now again, we just made a, we as an I made a very glib comment saying that we are going to introduce a partial wave expansion, okay? I'm going to introduce a partial wave expansion. You people should be very suspicious of this and tell me who allows you to introduce a partial wave expansion. You can't always introduce expansions, no? Only when can you introduce an expansion? You can introduce an expansion only if you know that it converges somewhere. Otherwise, just because I'm very good at using the chalk piece and I can just write some expansion, it doesn't mean that it's true. You have to make sure that the partial wave expansion is correct and it converges to the desired answer. And the nice thing about converging expansions is that if you truncate the expansion after a finite number of terms, it more or less approaches the answer correctly. And you can have a bound on the error because of the truncation. And you may say, what about if it is oscillating? Then it's not converging. Okay? So of course it could diverge in the sense that it just gives a totally wrong answer, or it could oscillate about the answer, and that's also not a good enough criterion for convergence. So we have to be sure that such a thing is convergent. Okay, so let me write this again. And once again, our friend Lehmann comes to our rescue and says that there are very nice circumstances under which the partial wave expansion converges. TILOS. And Lehmann says, see, again, we are using S, T, U, all these things without ever saying what is S, what is T, what is U, all these things. What is the physical region where S, what is the value of S, what is the value of T. So the physical region in the S channel is obviously when S is greater than 4, right? Because it's a real scattering experiment. And because T is related to cosine theta, and in the physical region, cosine theta obviously has to lie between -1 and 1, then T is forced to be negative, okay? So the physical region is when 0 so I should write over here, physical region for these scattering, physical region for S channel, S greater than 4m squared, T and U less than 0, okay? But Lehmann says that this expansion actually converges in the complex cosine theta plane. So it's in the complex cosine theta plane. And the physical region in cosine theta, can you tell me where this is? Somebody has to tell me what is the physical region for cosine theta. I just said it has to lie between -1 and 1. Okay. What Lyman is saying that is that this is the real cosine theta plane, and this is the imaginary cosine theta axis rather. Says that this thing will converge in an ellipse of which these two are the foci, and he also gives an expression for the semi-major axis. The semi-major axis being this. This is the semi-major axis. Semi-major axis for a fixed S. So Lyman says that when 0 is less than t less than 4, then 1 less than cosine theta is less than 1 plus 8 by s minus 4. I think that this is the right extremity. So this is the right extremity of this. You have to check some of these things because again I have got mixed up with some of these definitions. But the good thing is that we are allowed to take this expansion and make some sense out of it. Not only that, we are allowed to go beyond cosine theta equal to 1. We are allowed to go beyond cosine theta equal to 1. Okay. Now I want to look at this expression, and I would like to remind you that this L runs from where to where? Somebody tell me. It runs from 0 to infinity. Okay. Now we are going to try to argue that the bulk of the contribution to this is going to come only up to some capital L, and the contribution coming from L plus 1 and above is going to be very small. Okay. Now what controls the angular momentum channel in this expression? Now this is a function which is only a function of the energy, and it has a label L, but all the information about the angular behavior of this amplitude is coming from which object? It's coming from this PL, which is the Legendre polynomial. Not only is it coming from the Legendre polynomial, all that I talked about under this had to do with where this thing converges for the values of the arguments of this Legendre polynomial. Okay? So I need to say something about the behavior of this Legendre polynomial. And I just told you that our hope and expectation is that beyond a certain capital L for a certain energy, the contribution is going to be very small and will just not make any sense. So what should I do to analyze this PL of cosine theta in order to get a handle on what is the capital L beyond which there will be no contribution? What should I do to analyze this PL of cosine theta? I know I'm going on a bit too heavy today, so I should relax a little bit, let you also relax, and give me a very useful word for an analysis of this PL of cosine theta. It's a word that's very close to where we were 4 years ago when COVID struck, and we are all talking about asymptomatic conditions. So we are not looking at asymptomatic Legendre polynomials, but something else about the polynomials. You like the joke? Tell me, what property of the Legendre, see, it's dangerous to smile. Yeah, tell me what property of the Legendre polynomial would you like to invoke? You, I'm looking at you. Yeah. What property of Legendre polynomial? Not asymptomatic properties, but some other property that sounds similar. I got a smile even out of Vishajit today. Why don't you tell me? How about an asymptotic expression for PL of cosine theta? So we have brought in many things. We have brought in the fact that it's possible to extend the region of analyticity in this expansion, okay? And we have said it's possible to go beyond x equals 1. And we want to do something to analyze this thing over here using its asymptomatic properties. No, asymptotic properties. So let's write down some asymptotic property of this thing. And this is something that you can get from standard treatments of Legendre polynomials such as Erdélyi. And this also actually is very interesting. You should ask yourself, why is there an ellipse? Because we are always talking about radius of convergence of functions, right? Radius means that you implicitly assume that it is a circle and it has a radius around that circle. Why ellipse for this Legendre polynomial? Because the Legendre polynomial for it, -1 and +1 are equally good, okay? So the corresponding region of convergence of any Legendre series, not necessarily scattering amplitudes, is given in terms of an ellipse whose foci are -1 and +1, because that's the natural region of definition of Legendre polynomials. And of course, you'd like to go beyond that. So that's the reason why there's an ellipse for the convergence of Legendre expansions, in contrast to circles for other happy functions. So now TL of x is greater than, and this is an asymptotic formula, 1 plus 2x minus 2 to the power of half to the power of L, and then the constant, and then there's a 2L. When you see such things, because you may not be able to lay your hands on EDLE, but even if you can't, Mathematica has its own inbuilt function called asymptotic, at least in the recent versions of Mathematica. I strongly encourage you to use pirated versions the way I do, and you can find, this kind of asymptotic expansions for this. So here, now I need to do a PL of x, where my x is going to be cosine theta, and cosine theta, we already said, was t minus u by less than s to the power of n. And this is a statement that is given to you by axiomatic field theory, that this happens to be true, and we actually don't know and don't care what is this Sn. So this is an upper bound on this that is ensured by field theory, because in the construction of 2-point functions, 3-point functions, 4-point functions in axiomatic field theory, it is assumed that the field operators are what are called tempered distributions. Tempered distributions are those that go to 0 fast enough at infinity so that it makes sense to talk about integrals of these. It necessarily has to go, otherwise nothing makes any sense if nothing is bounded. So it translates into a bound on Ti of S, that it has to be smaller than S to the n asymptotically, but it doesn't tell you what is a n, okay? That is but you don't care for the moment. You know that this has to be true. Now, taking into account the positivity and all these things of these guys, of the imaginary part, and the fact that the Legendre polynomial admits an asymptotic expansion of this kind, and knowing that it is possible to continue the Legendre expansion beyond the real line where it is actually defined into the complex plane, allows you to make a statement on the imaginary part of the partial wave amplitudes, which reads that this is less than s to the n divided by c times the same 2l plus 1 to the half times 1 plus t by q squared to the power of half raised to the power of minus L. Now, the Froissart bound is related to a bound on the cross-section for asymptotically large energies, okay? Now, we are going to milk out of this inequality those quantities which are depending on n and nothing else. And we are also going to use some typical expressions that we are all familiar with from high school calculus in order to transform this into an expression that is going to be of use to us, okay? Now, I would very much like to turn this into an exponential. Now, if you look at the first term over here, now remember that q squared is going to be very large, okay? So if I want to do an expansion of this, I just have to work it out to the first term, okay? That's what I need to do with this. And then after expanding this out to the first term, I'm going to ask what is going to mimic it if I was to express it as an exponential. Similarly, I want to express this s to the power of n as an exponential. How can I express this s to the power of n as an exponential? I can take it as exponential of n logarithm of s, because the logarithm and exponential are inverses of each other, okay? So, and I'm only going to be interested in those parts of this expression which are going to contain some energy dependence. So after all that talk, now you will not disagree with me that I can rewrite this as some constant C prime exponential of minus L times 4 by S to the half, like this, times 1 minus epsilon of S, like this, plus n times logarithm of S. But S is a dimension full quantity, so I have to divide this by some other arbitrary energy scale that is denoted by S naught. Okay? So this thing over here has been replaced by something that looks like this minus L over here, and an exponential, so that this is going to look roughly like this. I think I've lost a term somewhere, but I'm going to, okay, I don't know what happened to the T. So now, after this, what I'm going to do is I'm going to now convert this imaginary part by using the optical theorem. So I want to plug this into the optical theorem and say that sigma total I total of S is again in these funny quantities 8 pi by nu times nu plus 1, the half imaginary part of Ti of St equal to 0. You'll recall that the optical theorem tells you that the total cross section is the imaginary part of the forward scattering amplitude multiplied by a suitable kinematic factor. I put the mass of the pion equal to 0. That's why it's looking like it is dimensionless, but it actually has factors of 1 by mu squared. Okay? Now, I want to use this expression and get finally the Froissart bound out of all this. So we are rewriting it. No, they give for both, but we want to plug it into the optical theorem to get something, some information on the cross section. A good question, yeah. Yeah, that's the thing. I think we eventually put T equals 0, but maybe in my transcribing this expression, I think I have kind of lost this T somewhere. Let me check over here. It's also there. I think when you do this exponential over here, where is the expression that I have? This one. It also comes out when you do the expression, but then you put that T equal to 0 later. Okay, when you're doing this thing over here and rewriting it, in the exponential also it is sitting there. Okay, I suppose so, but for the moment it's only on the total cross section. Again, good question. No, I mean we have to look up what are the known results on these things. Yes, yes. So this is in the units where mass of the pion is put equal to 1. Or yeah, so here mu is put equal to 1. Okay, so now I have to figure out what I must do with these partial waves, and I must say that I'm going to sum it up to a certain number of partial waves and throw away the rest. Okay, so that is a crucial thing that we need to do, and so let me see where that is. So now, of course, please keep in mind that we are adding all positive quantities. Therefore, the total cross section is bounded, total cross section is bounded by the partial sum. It has to be less than or equal to this partial sum. Sigma L equals 0 to L plus 1. Putting this equal to, I have lost some very important terms. Just give me 1 second. I have to fish inside my box to find the correct expression. Of course, it has to be at the bottom. You know, it's just a law of life. Okay. Just give me 1 second to rescue myself here. Where was I? Froissart bound. Yeah, so these bounds are coming exactly from this. I don't know what happened to this T over here. Imaginary part. Okay, this is all. There's some problem with the derivation given in this book. I didn't notice it earlier. But if you just stop over here, then we can translate this into a bound for this thing over here, which is going to produce the logarithm of this thing. Okay, so let me write down this result, and by the evening I'll try to clear this up and see exactly what is the problem that, that I've got stuck with. Okay. Now let me see over here. So sigma I total, so we have to plug this expression that I had over here, this one, and this is going to be 8 pi by nu L plus 1 squared, okay? So this is the crucial thing, this L plus 1 squared over here, which is going to give me a square of this thing, of this logarithm. So it says that the sigma I total is less than 8 pi C double prime times logarithm squared of S by S naught. So this is actually the Froissart bound, and later on Martin showed that for pi n is equal to 2, which gives a better bound on sigma I total of pi by mu squared times log squared of S by S naught. Okay. So this is the Froissart bound for pi scattering, and since we have the discussion, I'll just clear up some of these lacunae in this derivation. Okay. So I want to continue a little bit and talk to you about how to say something about the analytic structure of pi scattering amplitudes using all this information of crossing matrices and all these things, and to find the analog of how we wrote down and predicted the analytic structure of the form factor. We predicted that the analytic structure of the form factor is going to be very simple. It's just going to come from this J bar. There's only one variable over here in the form factor, whereas we have two independent variables for the pi scattering amplitude. Not only is it the pi scattering amplitude, but it's a system of isospin amplitudes. So what is the analytic structure going to look like? Okay? In terms of these simple considerations that we had, that of unitarity and analyticity, knowing the tree level amplitudes, how can you make some statements about the one loop amplitude using unitarity, okay? So that's going to be the next topic that I want to do right now. So let me assume a world where there are only S waves and P waves, and I'm going to ask you to help me try to create the pi amplitude at one loop, or the system of pi amplitudes at one loop of isospin amplitudes using the partial waves of pi scattering, only the S waves and the P waves, okay? So, yeah, 15 minutes, okay, that will be just right for this discussion. So, I'm going to ask you how to help me with this Ti of STU, like this. And I want to say that, look, there may be some constant for each one of these, lambda I. And then I want to have a part for each one of these that depends only on the imaginary part of the S wave. If there's only an S wave and nothing else is happening, then there'll be no T dependence at all. And I can say that it'll just be a function of S and nothing else. And if I say that there are P waves, it must have a cosine theta dependence. And we already have an expression for cosine theta here, T minus U by S minus 4. So can someone help me with this and predict for me what I'm going to get over here? What I might get over here? Well, I should get a T minus U. A T minus U divided by S minus 4. But also an amplitude which depends on S. So let me give it a name, and I'll call it Pi of U. A Pi of S, like this, okay? Now you people should not be satisfied with this, because this is not like a form factor. It had been like a form factor, you would have just said, yeah, fine, everything's over, we can go home. Now we know that all these cross channels also exist, okay? So what happens if you're going to cross channels? You have to be able to permute S and T so that there's an additional contribution to this function coming from such crossing. So how do I do this crossing? Well, to do this crossing, I have to use the crossing matrices. And let me do that. What are they called? CST of II prime. But the analytic structure should remain the same in that channel. Now I have crossed the SNT channel, so I should have an SI prime now of T. I've crossed S and U, so I should S and T, so I should get S minus U, and I should get a P I prime now of T. Okay? Am I done? No, I'm not done, because we are not allowed just to cross between S and T. You should also have to cross between S and U. So there has to be one more contribution to this from the here, which is going to look like C I prime now of SU. The same function Si prime, this time of U, and this time it will be S minus T. There's also a factor of 3 coming from the Legendre polynomial, 3 times T minus S Pi prime of U, like this. Okay. So this is very nice. So this is assuming that there are only S and P waves. Only S and P waves. So you see, life has already got much more complicated compared to when you had form factors with these scattering amplitudes, because there's so much more information in scattering amplitudes corresponding to this. So then, okay. So this gives you the Ti of STU like this. You know explicitly what these matrices are. So from this, you can make a prediction for what is A of STU. How do you know what is A of STU? Well, we already wrote that. It's 1 by 3 T0 minus T2. And if you do that, you get an expression for this that looks like this. It will look like a new function that looks like 1 by 3 W0 of S plus 3 by 2 S minus U W1 of T plus 3 by 2 S minus T W1 of U plus 1/2 of W2 of T plus W2 of U minus 2 by 3 W2 of S. It's pretty amazing that such relations exist and can be predicted by just simple use of unitarity and So these are 3 functions. So just these are all different functions, linear combinations of these S's and these P's, so that you have 3 functions of single variables, 3 functions of single variables, and I'll tell you what they are in a minute. Single variables whose imaginary parts are given by imaginary part of F00, imaginary part of F11, and imaginary part of F20, obtained from the tree level amplitudes. So this is at one loop, where these are obtained from tree level relations. What I'm trying to say is that this is the analog of what I had here for the form factor. For the form factor, it was possible to predict the analytic structure of the form factor. It's a function of only one variable. Just from the analytics, just from knowing the imaginary part, there's the imaginary part which I have erased now. Yeah, this imaginary part will allow you to predict the structure. Okay, so there's only one function, J bar, and from that we are able to get the whole thing. Now here, and of course, you also need the tree level amplitude of the pi-pi scattering. So here, from the tree level amplitude of the pi-pi scattering, you have to be able to produce imaginary parts of the 3 lowest partial waves, and from those, you can predict these functions up to polynomials. So that's the thing, you see, just going from form factors to scattering amplitudes, how much more complicated things have become. And it brings in the full machinery of crossing, of isospin, all these things, which is what I wanted to emphasize over here. So let me give you an example of a decomposition of the one loop amplitude, which is also covered in the earlier class. So W1 of S, this one over here. So this is ASTU. ASTU at one loop will necessarily have to have a structure like this, where we are retaining only SNP wave partial wave amplitudes, because that is what chiral perturbation theory is telling you, that up to one loop, it's only these partial waves which have imaginary parts. So you can actually use it to predict the structure of the one loop pi scattering amplitude just based on unitarity and analyticity and crossing, using the information of the scattering matrices and knowing that you will have three functions of single variables whose imaginary parts are given by the three lowest partial waves. So let me just write this down. W1 of S is given by 1 by 576 pi f pi to the 4 times S minus 4 times J bar of S. You see, our friend J bar of S is back in pi scattering also, because it's only one loop. So it's like this, right? So this is the same one loop amplitude that's going to show up. That's the reason why I derived it in my first class from Ramon. It's the same J bar of S that shows up again and again at one loop when we are doing just pions and nothing else. Yes, because chiral perturbation theory, which is telling you that at tree level, you just have this linear amplitude. This is not chiral perturbation theory, but the approximation that only SNP wave absorptive parts are present at this level. If that is so, then this is dictated by crossing symmetry. The crossing symmetry is actually telling you to write this down in terms of the isospin amplitudes, crossing matrices, etc. And if you take this and then use this expression over here, then you will be able to re-express it in terms of three functions that look. Even here, there are only three functions, no? There is, well, there's more than that. But somehow it all disappears and you end up with just three functions of single variables. So this is part of the things that I wanted to discuss over here. And now by the time it's 4:30 in the evening, I should repair my derivation of this, of the Froissart bound. The problem is each of these books is having its own notation, and just going from one book to the other had just made a disaster of this derivation. It's not such a disaster, I just have to fix it and spend a few minutes re-deriving it correctly. So this is one of the things that I wanted to talk about. I have many other things that I wanted to talk about. Maybe if we have a little bit of time in the evening, I could spend some time. Any questions? Yeah. I started out with S-channel amplitudes. You could have started out with T-channel amplitudes. Now I can go to the T-channel by multiplying this whole thing by CST also. So that's a good question. If you multiply this whole thing by CST, you'll see that the CST squared will become an identity. Therefore, you'll get the same expression as what is up here with T replaced by U. And this thing, the product of these two is going to be UT, etc. Not for the, yes. The Lyman ellipse comes from a physical consideration. So he says that let us try to extend it, and it comes from all the assumptions of axiomatic field theory, and it also has the information on the spectrum of the theory. So where it converges, this particular number that I had, which is 8, is associated with the lowest singularity here is associated with 3 times m pi squared, okay? So there's a physical assumption also that tells you that it can only converge here. And there are different results for different processes. Pi k scattering has a different Lyman ellipse. Yeah. Yes. It's all very complicated stuff. So this is like the simplest, and this is the result that is known for pi scattering. And other processes like pi k scattering and pi n scattering, each of them has its own Lyman ellipse. There are 2 mass scales over there. And then you have to know what is the lowest or the nearest singularity, which is what is going to limit the right extremity of your Lyman ellipse. to say that this asymptotic thing is greater than for x greater than 1. Okay. Yeah, thanks. I should have written this. It's actually very intricate machinery. This was all known to the generation that is no longer here, or actually 2 generations ago, people knew these things inside out. But now it's all there in a bunch of very good books. As I said, it's like an archaeological dig, and I'm not an expert on these things. It's just what I know is what I know for preparing for these lectures. It is all, just one sec, it's all implicitly used, because supposing you want to introduce a partial wave expansion, so you say, you just give some inequalities saying that this thing converges there. And nobody really has gone back and checked when it is true, when it is not true, etc. There's this book by Martin and Cheung, which is very good, which has lots of exercises at the back, which are problems that are worth doing also, if you have the time to do these things. Yeah. Which one? Here? Scattering of equal mass. The contours. Yes, this one. Yeah, and this is for the youth channel, it's the 2 pion threshold. But this is at a non-zero value of t, right? So you have to see SR over here. So U equals 4m pi squared, but S plus T plus U equals 4m squared. So let me see. S plus T plus 4m squared equals 4m squared. So this cancels out. So this S equals minus T, something like this. I have to check exactly what it is, okay? It's because of this constraint that I don't immediately know exactly where it is. What we do later is we are going to redefine these things and write everything as if it is coming from a right-hand cut, keeping in mind that there is the U is lying somewhere else for the physical region of the S-channel scattering. The physical origin is that the optical theorem tells you that the cross-section has to be greater than 0. The physical origin is the optical theorem, which tells you that the imaginary part of the forward scattering amplitude is equal to the total cross-section up to some factor of 4 pi by k squared. Yeah, the equality is when the scattering is elastic. And when you introduce this additional eta parameter to account for the inelasticity, and you plot it in the Argon plot, you see that the curve goes inside the Argon circle, and that tells you that the imaginary part is larger than the absolute values. These are all features of scattering theory. It has nothing to do with pions or anything. Even in quantum mechanics, it's like this. Any standard book like Merz-Parker and so on will have exactly all these nice plots. Are we okay? Anything else?